This is a really good question. It really tests that you've grasped the concept of dealing with matrices, systems of equations, and also solutions, systems of equations. But if this is not familiar to you and you don't know how exactly you should approach this problem, then let me show you the way. This is the system of equations. Let's worry about choosing the alpha later. For this system of equations, I can write as an augmented matrix. So I can formulate this as an augmented matrix with the coefficients x1, x2, and x3, 1, 1, and 2. And then for x2, I have alpha, minus 1, and minus 2. For x3, I have alpha here. There I have 3. There I have 0 in the first equation. Now, I still have not augmented my solutions to this matrix. So let me do that now. By augment, I mean I glue the solutions to my system. 1, minus 1, minus 2. I don't like the green color. Let me use the purple one. I think this one's nice. So this is really how it reads off. So 1 times x1 plus alpha times x2 plus 0 times x3 is equal to 1. You could proceed similarly for the other 3 rows. So it is a way to encode our system of equations in a way that we can read and handle as well. So we would like to proceed with some Gaussian elimination. Gaussian elimination entails eliminating variables. For example, you have this equation and that equation. This one has x1 and this one has x1. So why not multiply this equation by minus 1 and add it to the second equation? If you do this, then your x1 is going to vanish, right? Then it is very good. And let's say you want to do the same thing here. So you multiply by minus 2 in order to make this a 0, to make that a 0, and to keep this as a 1. The goal is really to have x1, x2, and x3 in the following format. This one on the right. And why is this useful? Because if we have it in this very specific format and we read it off like we did here, but in the reverse direction, then we can say x1 is equal to 1 times x1 is equal to something, 1 times x2 is equal to something, and 1 times x3 is equal to something. And the other variables are 0, they're eliminated, cancelled out. So this will be very nice. Wouldn't you agree with me on this? Well, I hope you can. So we proceed as mentioned a few moments earlier with this setup. Now I have some sort of tool that will help us not make mistakes, because I think the main problem with Gaussian elimination is that it could involve lots of mistakes. So what I'm going to do here is I'm going to erase these old values which I've used from another problem, and I'll take the row that I want to multiply by, which is this one. I feel like it would have been easier if I just wrote them down. But anyway, this is the row. I want to multiply this by minus 1. When I multiply this by minus 1, I get minus 1 minus alpha, 0, and minus 1. I want to add this to the other row, which is the second one. So I copy it. It's 1, minus 1, 3, and then minus 1. When I add these these new entries to the other row, I will get a 0 here, -1 minus alpha here. Here I'll get 3, and here I'll get -2. So I can write this as follows. I'll get rid of the x1, x2, and x3s, because I don't want them to be distracting for us. Our new values for the second row are the following. And here we have a -2. You just need to do this one more time. If I multiply by -2, I get -2. Here I get -2 alpha. Here I get 0. And here it is -2. I add to the new row, which is the third one, 2 minus 2 alpha -2. I get -4, I get alpha, and here I get -2 alpha -2. Here I get -2 plus 2 is 0, because they cancel out. Remember that I made this very specific choice so that I can cancel the terms out. So that was the established public goal for us with this problem, or at least with this very specific step forward. So these are the new values we have for the third row. We need to do this, I think, 1 or 2 more times. The goal is to make even more zeros. Here I have -1 minus alpha. I'll try to make zeros. I'm not sure if this is possible, at least with this choice. So we need to be careful with our next steps. But I see something that's very interesting already. I see that this is -1 minus alpha. This is -2 alpha -2. So there's a factor of 2. So perhaps I shouldn't immediately rush and make all of these be equal to 0. Let's try to make this 0 and see what happens. All I need to do is I need to multiply by -2. If I multiply this row by -2, then this set of entries becomes positive. If this set of entries becomes positive, then they'll cancel out this specific term. Let me show you how this will unfold. So this is my row. And then here it's -2. I multiply by -2, I get 0, stays as it is. And this becomes 2 plus alpha, 2 alpha. This becomes -6, and this is now 4. I want to add this to the third row, so I add the third row here. -2 alpha. Here there's alpha, and here there is -4. So isn't that amazing? We get even another 0 here, 0 there, and a 0 here, as intended. So originally we were planning to have a 0 here. We have another 0 extra. And this was always going to be a 0 because we're adding 0 to 0. So it would have stayed unaffected in any case. Sorry. And here we will get alpha -6. So perhaps I should write this down. Alpha -6. Now, by the way, this draft is optional. You don't need it for anything. We're just using it to compute the values and to try to make progress with the problem. And that's all. So here are my new values for the final row. They're 0, 0, alpha -6, and 0. And now I would like to strategically take the moment now to read off this equation. What is this equation telling us? Let's see. If I focus on just the third equation, and read it off as I usually do, it's saying that 0x1 plus 0x2 plus 0x3, well, not 0x3, alpha minus 6 of x3 is equal to 0. This is, of course, 0. I don't need to write it, and this is, of course, 0. So this is what the equation is saying. Now, let's go back to the original setup. We have the freedom to choose alpha, and this is what's so powerful here. We can choose alpha to be any number we want. And we want to choose the alpha to be the value that will ruin our system of equations. So the only reason Gaussian elimination works is because we make a preliminary assumption that there is a solution. So if we are able to sabotage this equation and make a contradictory statement out of this, then this will be great. I think it is very tempting to choose alpha to be equal to 6, because then if you choose alpha to be equal to 6, then it just means that 0 of x3 is equal to 0, which means that x3 can be any real number. So x3 is the number that satisfies 0 times x3 is equal to 0, and this is why it is any number, because any number can satisfy 0 times this number equal to 0. But does this help us? Does this help us find no solution whatsoever? This is a good question to ask. Well, let's try to plug in the minus 6 and see. We'll get x1 plus 6x2 is equal to 1. I'm reading off the first equation and plugging in alpha. And then this will give me something. And for the other equation, it would read off as minus 7 x2 plus x3 is equal to minus 2. x3 can be anything. We already talked about this. Perhaps I could cancel out the minus 6 and the 7 somehow. So I multiply by 6 over 7 and I add, so I get 6 over, so I get x1 as it is, and then minus 7 times 6 over 7 x2 plus 6x2, 6x2, and then I get, of course, don't forget to add 6 over 7 of x3. You'll get 6 over 7 of 2, of minus 2, plus 1. So there seems to be a solution here. It doesn't seem like we've reached any sort of contradictory statement. Now, this looks ugly, I agree with you. And what I'm trying to do here is I'm just trying to explore this expression. It looks okay. It doesn't look like, alpha is equal to 6 is going to cause us, any trouble, well, as intended. And then probably we should continue investigating. So we do this. Let's say we even, add this row to that row. So we multiply by 1 and add it. If you take this row and you multiply it by 1, it's just the same thing. And if you add it to the first row, which is 1, alpha, 0, and 1, you will get the following. So I think it is good if we have to worry less about this alpha that was here. So 1, minus 1, 3, and minus 1. It's looking good. And now let us even let's think about what we would like to do next. I think it would be a good idea to sabotage this by making a 0 block here. I think a 0 block would ruin our pivots. If there's a block of zeros, then we can't really have the pivot, which is 1, that we're looking for. And then it would sabotage this construction. So how can we get a 0 here? If I want to set minus 1 minus alpha to be equal to 0, then my alpha should be equal to minus 1. Then let's see what happens when we plug in alpha is equal to minus 1. Let's see what matrix we'll get. Oops. This would imply the following matrix. Here we will get a 0. Minus 1 will give us a minus 7 here. And I think this is, so minus 1, minus 6 if you're wondering. And this is really what sabotages it, because watch this. Let us read off the last two equations. So if we read them off, we will get 0x1 plus 0x2 plus 3x3 is equal to minus 2 on one hand. On the other hand, you will get that minus 7x3 is equal to 0. Contradiction, right? Because this implies that x3 should be equal to minus 2 over 3, and that implies that x3 should be equal to 0. So, and obviously, the last time I checked, minus 2 over 3 is actually not equal to 0. So I really appreciate how I led you on at the start to choose, to think that the value would actually be alpha is equal to 6. It's not. And this is really how you make problems. This is how you sabotage the system of equations. You make a block of zeros, like a 2 times 2 block. This is problematic because in this case, in a 3 times 3 matrix, of course, it's problematic because it cuts the diagonal, you could say. You don't have this, this hope of getting, x1, x2, x3 is equal to something is now shattered. And if we reach this, this block of zeros, then we are always able to get a contradiction. Well, not always, but often this is problematic. And if we get a contradiction, then our original assumption, our original preliminary assumption that a solution existed for this system was false. Because if you build your foundations on something that is wrong, no matter how far you keep going, you will eventually, reach a dead end. You'll reach a contradiction. So probably you shouldn't. You should take this as life advice. Important mathematics.